Okay, good morning, everybody. Today, I'm very happy to have as our lecturer, Dr. Rabih Amhaz, who is a very dear friend of mine and a long-term collaborator. He is coming from the University of Strasbourg, where he is the lead AI scientist there at the Icam laboratory. And he'll give you more details about exactly what he does and what he has done to get here. He has been in many places on the planet, including Azerbaijan, where he founded a master's program, but also here. He'll also give you some details about that. And today will be a lecture about engineering, but also a little bit of behavior and neuroscience. It's not absolutely his topic, but it's coming from our collaboration. So I would urge you also to join the meeting online, also for those that are here, and turn off your microphones. And whenever you want to ask questions, please turn on the microphone and then turn it off again, such that the online audience can also hear it. Okay, thank you. So please, Rabih.
Thank you, Dr. Samy. You can hear me well, I suppose. Yes. Thank you, Samy, for this invitation. Thank you all for being here. Thank you for those audience online. So my mission today in Fribourg is to bring for neuroscientists and for the digital neuroscience that you're following the maximum insights from multimodal AI. And before that, just a small introduction, because today I'm working with as a researcher lead at Icam Engineering School in Strasbourg, and with Icam Laboratory with the University of Strasbourg. And before that, I was the head of the digital department. And then before that also, I built some master degrees, professional master degrees about Industry 5.0 or the industry of the future with all the technology that we can introduce there. And before this experience, it was a huge experience after my PhD in image processing, to build a branch for the University of Strasbourg abroad at Baku, Azerbaijan. And before all that, and all my studies in France, I was in Beirut to study engineering. So I was a telecom engineering, and then I continue my journey in the computer science field and informatics, and more precisely in the algorithms. So the project that we work actually on are project related to still image processing to detect the cracks and road maintenance, and to collaborate between different AI to vision AI to detect the cracks and to do road maintenance. Mind 5, that this project I will present today to you more in details, in deep. Some document to graph learning also projects. We work on reading the mind maps of the students to couple the teachers with some additional tools. And we think that mind maps, unstructured documents are really challenging topic to work on, and we are working on this. And also, because my mother language is Arabic, I work with Arabic AI, Arabic large language models, and specification on audios and other tools. So what we will see together today in this session, we will see how much neuroscience and digital neuroscience, at least the neuroscientists that they were really tech-oriented, influence AI, and this will inspire you, I suppose, for the future, for your future career and for your future project and involvement. And to influence AI, we need to know what is AI, what is feasible today, what's not feasible, especially how to choose the right models for you as a digital neuroscientist, and that you will work with a lot of data. Then what is the relation between multimodal AI and the complex system, or the neuroscience and the complex systems? Why? Because I will introduce you the main challenge today in AI, in AI models are the challenges of the graphs. And this is the breakthrough when I say attention, revolute, everything. We will see together for sure that. And for sure, I will present the experience that we are doing between University of Fribourg and University of Strasbourg and Icam, precisely as engineering school. What we are really talking about what really we are talking, because if we say, okay, we want to talk about artificial intelligence, but what is intelligence in this case? Who defined the word of intelligence? We are just hearing all around the media, AI, agentic AI, agentic AI, agentic AI. And we still don't know who made the definition of the word intelligence. There is philosophers, psychologists, neurologists, neuroscientists. There is a lot of definition out there. And in addition to all that, came the whole teams of computer scientists and say, yeah, let's define intelligence from our perspective. And let's take these definitions that are really everything and anything and all in the same time. Like for classical definition, the complex definition, let's say, it's to understand, to learn, to reason, to solve problems, to adapt. The neurologist or the cognitive, on the cognitive aspect, they start to talk about the G factor. G factor today, it's not used anymore, almost not used, if the neuroscientists agree with me. Then cognitive reflection tests. And how we can evaluate if the kid is intelligent or not intelligent, if the guy is intelligent, not intelligent, IQ test, blah, 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 blah. This is intelligence. And the common aspect of all this, it's a complex system. It's even social system, like the complexity of adaptation individually and collectively, socially. And this is intelligence. This is the common terms of intelligence, at least. But computer scientists stay with one definition. Stay with the aspect of, okay, we want to stimulate the human brain because he's intelligent, he's evolving, he can adapt to any situation, he can adapt to any social aspect that's happening. So let's reproduce, and they mention it like this, but then they didn't do it really. Let's reproduce the human intelligence just by mimic what the human is doing, by problem solving methods sometimes, by doing other type of algorithm that we will check, etc. And first, it was really computing without even any aspect of memory, right? Because we started just with classical computing system that there was no memory at all, and we were like, consider any program, especially in the 50s, okay, any program as intelligent program, even if it's just switching the light because we pass by, right? This is what we call it today, narrow intelligence. And because all the technology wasn't there to help us with these systems. So the computer that was rooms and big rooms that transformed to laptop and to small processors, it was really the intelligence at some point was just the computing systems. And we need to know this history factor or history propagation of things, because the propagation and the history of the AI will lead us to say, okay, this is the weakness. We still with a lot of weakness today. So computing, automation, the narrow intelligence, general intelligence, and now everyone is talking about the super intelligence, right? The AGIs, all of them, especially because they want to create more and more hype, and hypes means business, means money, and they can like simulate all that. But in fact, what's happening? At the beginning, it was the beauty of the start. In the 50s, especially in the 50s, they started to use this term, and we will see who did it. And then they face the problem of the technology, the computing problems. And no one was able to compute everything and to really do even simple things. Then expert system came on, and we imagined that by doing graphs and by noting rules for everything, we can make rules for everything and anything. And using these rules, we can do something very intelligent. Then, no, we cannot make rules for anything and everything. We are so complicated. We are doing a lot of stuff in the same moment. We are building, socialing, communicating, receiving, all at the same time. We are doing reporting also. I'm not doing reporting right now, at least. And then the hype starts in the 2010s and after, especially with this system that managed because of what? Because of web. On the web was more realizing what really we do in life, and what we do exactly in life. We social, we communicate, we send. Today we send to each other photos, and it's obvious, but before it wasn't like that, right? And we had this web aspect that made a lot of photos on the web and interaction, text, photos, cats, dogs, etc. And finally, scientists decide to use these images to select if it's an image of cat or dog with deep learning. And then we are not stopping evolving very fast since this deep learning models for vision models, right? And then all this story happens with not like a huge conference with hundreds or thousands of persons that appear there. John McCarthy was organizing a conference and was waiting for a lot of people for this conference. And in reality, it was like a workshop, just workshop of six that stayed from the beginning until the end. Here in the photo, they are 7, but in reality, they didn't stay 7 persons for all this conference, international conference that they organized. So they just stayed 6 persons. And their mentality was, at this point, is to replicate the human cognitive behavior, the human cognitive capabilities. And we are still using the same term today because we are not able to do all that really and efficiently. So you already know narrow intelligence is already existing, and it's all about everything about switching, etc. Alexa, Siri, all the chatbots that are very narrow to us and can chat based on some even expert rules. And then we have the artificial giant intelligence that are more and more getting all the knowledge around the globe, or what is text, images, etc., and using that to make models like DeepSeek, Queen, Claude, Gemini, ChatGPT, and others. They are not alone. And they are all speculating around the whole super artificial intelligence that in the theoretically, yes, we can. It's already here in theory. But in ethically and efficiently, it's not yet, because even now, by the largest models that exist out there, okay, they are eating all the data of the globe, and they are not managing to be the only tool that we use daily or weekly or monthly, right? Because they will seek again. At some moment they will seek real data that are not generated by the AI. And we will fight later on, not for oil and gas only, for oil and gas, for energy, and for the data, for the real data, for the real cells, human cells, let's say. But it's still a myth, right? Neuroscientists inspire AI, and I would like to ask you how they inspired AI. all start with the perceptor. Okay, after the conference that was in 56, because it was like talking, imagining ideas, etc. Perceptrons came out, and it was really to imagine that we have cells, and these cells can be transmit the efficiently if it's an X in the pixels, and it was still with the really old models of computers time at this period. So it was by coding on papers, and I forget the name of the tool, the Zagraph. And then Hebbians, because you mentioned it in the polls, this is true. Say, okay, so synapse collectively spike something, and when the rule is when they spike together, they wire together. Okay, when they fire together, they wire together. This change the rule again. Why the okay. You can see it here, but I cannot see it on it. Yeah. So they wire together, and still this is not a political point that make the aspect of neurons. Okay, this is just also some noise in the room to wake up those who are not following and don't like the history aspect of the things. And then the hierarchical vision models by convolutional neural network that comes and start to say, okay, we can divide the image to small blocks, and these small blocks, by putting multiple layers one after the other and activating these layers, we are able to know the numbers, for example, the handwriting, and like everything was about how to mind this. Writing tree, what will look like. It's so difficult to see that the graph, the activation graph behind it here. Writing one, writing different letters, reading these letters with OCR process and Minset as images. It was really the challenge that changed a lot of stuff in the 80s and later on. And then brain-like learning. We like rewards. We write sugar at some point. We like to get this feeling of, yes, we achieved something. We are winning when we are trying to do things efficiently with a lot of rewards that come back. So we learn with the reward system. And now they are emulate even chips to impulse directly, to interact with the neurons directly with the neuromorphic chips, modern neuromorphic chips, which is also a challenge. It's an ethical challenge and moral challenge and scientific challenge at the same time. We can push, but what will be the next phase of this pushing? Yes, these are the history of, from computer science perspective history, from neuroscience that inspire AI models until today, but in reality now what we are really using. When we say deep learning or learning, machine learning, we are talking always about, is it supervised learning, unsupervised learning, is it reinforcement learning? So if we have labeled data, we can use the supervised learning, like here, to select cat and dogs. If we have unsupervised or unlabeled data, like in these images, can we categorize these images between these cells, these membranes, between group A and group B, yes or no? Yes, we have some features different, and AI learns about these features, these difference alone. So unsupervised learning because unsupervised data. And then the reward system that we were just talking about. If I say sit to a cat and it sit and I give her a reward, it will repeatedly do it because it will learn that this way I will eat more, I will be happy, I will make more, right? So I like this schema of AI to resume like every aspect that we can use today, from machine learning to deep learning, NLPs, robotic, computer vision. These are the category each time. And this graph was done by my PhD student, Raouf, that I would like to say hi and good luck for him because it's his last year. So how we will choose from this? Okay, the catalog today is huge. And how we will choose if it's only machine learning or really we need deep learning, or let's put NLP and LLMs and VLMs, vision language model, or genome language model today. In our lab, they have a PhD student that will also finish in a few weeks or next week. And he's doing genome language models. So how we will choose for you? Can you tell me based on what? Yes. Based on the task that you have to perform. The data type. Thank you. There will be always the same process, actually. Thank you for this small exercise. It's done, and the AI robot is happy, kind of. And so the challenge is, okay, we saw it, how we really choose them all. It's not only about engineering. It's not only steps. It's a very scientific aspect that we need to evolve with it step by step. So, especially for your case, we can say, let's start from the paradigms. And there is no one definition for that. For example, is it knowledge-driven, symbolic? Is it probabilistic? Is it data-driven because of the data? Because we have data, we need to do something with it. Sometimes a lot of commercial aspects is thinking like that, thinking from these paradigms, starting from data. Is it interaction-driven? So reinforcement learning is important, and the dynamic aspect of the things make us push us to models in the field of reinforcement learning. Or is it object-centric? This is the huge discussion today between researchers. Is it object-centric or neurosymbolic hybrid AI that we should use? So if we are with the knowledge-driven, we know, this is my expertise. This is how I do things. And I don't want just to replicate, my digital twin. And this is how always I work in my projects. So symbols, logically, this is how I work. I do the reasoning by logic sequence and some expert system. And there is influence for the history on these paradigms also. But the constraint is the satisfaction at some point. We cannot be satisfied with expert system until the end. And it's not enough. So we say, okay, let's do the probabilistic aspect. Everything is probabilistic. Reasoning should be influenced by the Bayesian aspect of the things. We are never sure 100% of something, even if it's a procedure. We are humans, we are biology, so things evolve. But if we work everything with uncertainty, okay, this is also a problem. It's at the same time a positive point and negative point. So Bayesian model or Markovian models that you use a lot in digital neuroscience, I suppose, I discuss a lot with Samy, and you use it a lot. So yeah, but why? Why we should stay with this phase of probabilistic phase? Maybe yes, we need it sometimes. We don't another time, and etc. We are not all the times probabilistic. Like the probability of changing my words during this presentation was so high, but I fixed my rules for this presentation, and then I just leave a small aspect in the probability aspect. Data-driven is always pushed by, yeah, we have a lot of data. We can scrap everything on the internet. We can scrap all types of the images for industrial objects, for example. So let's do models about that. And large language models was like driven by data, driven because we have a huge amount of data that we were able to scrap. It was 450 gigabytes of text at some point. This is at the beginning. Today we are with more, but at the beginning it was like, yeah, wow, 450 gigabytes of text. So let's do something with them, and they built the first model of GPT 3.5, right? And then they iterate over it, and they added more and more and more data and more parameters. And we will talk about these parameters just in a few minutes. And then the interactive aspect, the interactive driven paradigm with reinforcement learning, for sure, it's always used with gaming. It's very used with gaming, and it's normal because gaming is already in this mentality of, yeah, rewards, let's play, let's win, and we want to improve dynamically reasoning and dynamic transitions in the data, and there is no fixed state, let's say. So it's a state, actions, and the transition between. And today, for the rewards, it's a lot about robotics. Okay, so reinforcement learning for the robots is done, and then the robot is given out there humanoid to walk efficiently, etc. It's all simulated with millions of digital robot that is simulated, and then we bring this knowledge, these rewards, on the real robot that comes and join our life. And then the structure-driven or neurosymbolic AI, and here is the debate, the huge debate today between, should we do AI most of the time driven by the object? Should we do AI driven by the context only? Should we do AI like mix of these, because there is the object influence the context, and the context influence the object, etc. The interactive mode, the hybrid mode, combining the symbolic and the expert system with even the object's word and the patterns in the context. And this is, at least this is what we seek for we are the team that work on this neurosymbolic plus hybrid AI, because we work with complex systems. I always see society and even biology and even everything as a social interactions, and this means the context is important, the individual is important, and the combination of both should take place, not just object-driven AI. So, and this is just a representation to try to choose. And only by iterating, only by trying and failing, maybe, or trying and winning at some point, and by doing what is really the task, the context that we are working with, we are able to choose our model, our best model. We will use NLP now. We will not use NLP. We will use computer vision now. We will not use this aspect, and so on. And we combine computer vision with NLP to do that and to simulate this activity. Always is about thinking. Thinking is already like using our neurons, using complexity, and using complexity means we should know what is the definition of complex system. I'm coming from a team which the title of the team is complex system and bioinformatics. So complex system is our core vision for every aspect. I see the industry as a complex system. I see the society as a complex system. But what is complex system? Many interactions, individual interactions, but the overall behavior is not controlled. This is what happens with our genomes. This is what happens with epigenetics. A lot of interactions. Sometimes we see that there should be a problem. Two twins with the same, like almost same everything. We have something with one and not the same with the other. They were like evolving from the same cell, right? So it was divided at some point, and things happens. There is a lot of interactions in the complex system. There's three priorities. When you see a lot of interactions, a lot of input, output, a lot of things, interactions, non-linearity, not because we are thinking collectively today to solve the problem X, we will be able, because we are 100 or we are thousands or we are millions, we are able to solve it, and we see it. We don't know. Sometimes it converges, it works, sometimes not. Why? Is it because someone listened to something that was said at this moment and managed to replicate the experiment and do something? But yeah, it's like there is the example that we were discussing yesterday, and I was trying to understand from neuroscience that I will show you just after. And then there is emergence somehow, but we don't know why. So a complex system is the story of multi-agents or multi-things interacting together on the multi-scales and non-linear behavior that is appearing, and we don't know why, and some convergence in the aspect. So examples of that: neuroavalanche in the brain. Okay, neural avalanches. He just described it to me in few sentences, and it's really a huge example of what's really happened. We don't know why it happens like this, and how many neurons we need for it. We don't know. It depends on each one. It depends what did he eat in the morning. It depends on what happened. Weather systems, global air traffic network, tumors grows, and immune system, all related to this complex system. Like the movement of these the movement of these birds. There is no way to know if it will go right. They will do circles. They will do cylinders. They are just moving and influencing each other collectively, like without knowing who's influencing what and how. They are just collectively moving as a complex system. And do you remember about how we choose AI models? It was what we need in the AI models. I don't want to lose you. Graphs. We need to represent the AI models. We need to represent the context, representing interactions and non-linearity means we need something that I cannot draw it on this table efficiently. I cannot. Interactions between individuals, and we want to to show the non-linearity things of things, and we want to represent complex systems and these data that influence everything everywhere in all that. So we think that graphs are able to do this representation correctly. Okay, and flat data, okay, machine learning managed the flat structure of data, audio, text in the past, for sure. They will show you what was the breakthrough. And this flat data are really managed by the machine learning classical aspect, okay? And there was no loss of information in the relation because it's already flat, it's already drawn on an image, so pixels are near to each other. And okay, nice, we can use machine learning and we can learn this convolution between the pixels and so on. But if we need more complicated aspects, okay, more complicated ideas that comes, more complicated interactions that I want to draw, we cannot do it with a flat systems. So what we can do, if it's also the dynamic aspect of things, it's not flat, is to represent graphs and use graph learning, and I will show you examples about that. Graphs are just nodes and edges that are represented like this. For each node, we can represent anything we want. And we can represent complex things also. It can be like one node can represent like groups of points or a cluster. The cluster, I can resume it to one node, right? Community subgraphs levels. So the node can hold data and varieties of data, and the edges can also hold data and vectors of data, not one data. And this is how we had this revolution of the block of attention. So graph embedding, message passing models, graph generation models, graph neural networks for dynamic aspect, it was all about encoding nodes on the embedding space. So we have the network that can represent everything and represent really complex things with a lot of interactions. And then we have the embedding in the space of the embedding. So we pass from graph representation, which represent this complexity, to, yeah, we can embed this complexity to vectors and to matrices, and then we can iterate over this representation, mathematical representation, to do clustering, to do node classification, to do link prediction, and graph classification, and so on, to do some predictions in the model. And this is how, in reality, transformers did. The attention model and the number of parameters, when we say 1 billion parameter, is because one word, which is thank, right? One word is represented on 1 billion value, a vector of 1 billion value. Why? Because we want to link thank to all the words in the dictionary and all the words in the different languages also. So it's a huge connection with thank and merci, huge connection with shukran, and so on. But it's this, when we say 1 billion parameters, 3 billion parameters, 7 billion, you can download the weights on your computers for the 7 billion. When you go up, it's harder. And everything changed in reality based on this this aspect of, yeah, we already have images and pixels. We represent pixels and we change the layers to represent the convolution aspect. We represent it also with a speech, but what we didn't yet solve totally and for every aspect is the networks, and not only these flat things, text and images. No fixed ordering, complex interactions. We don't know. Group red nodes are the nodes that activate the thing or emerge or converge to something. And I will pass a little bit fast on this aspect, I suppose. Or you have questions? You were saying that in philosophy, the emergence comes from the Bayesian and collective consciousness on subtopics and stuff like this, right? And this is exactly what our complex system representing. So complex system can represent like the social interactions and social behavior and why these groups emerge and done some cluster of idea, like now it's really emerging and then covering or converging for the others or influencing the others. There's already studies, like for example, if in a meeting, before you go to the meeting, you have 10 people, right? And in a 10 people, before the meeting, you convince only 3 of the 10 to go with you to the meeting, you can influence the 10, right? We don't know why. Sometimes it's pass, sometimes it's not, because there's someone who has a veto somewhere, he has his personality, etc. But usually we are able to influence the others this way. And this is what the social groups do sometimes to collectively or with some groups impact the society with some ideas and win the elections, win some social fight about roles, etc., etc. So how computer science can represent that? I can tell you that simply we can represent the graph of individuals and their ideas like this. We can cluster based on the ideas and see how much persons that they are. If they are like very near to each other, the red dots. If they are near to each other, maybe they will not influence a lot by giving maybe impacting this one and this one and this one. But if the red dots was distributed differently, probably they will make more red dots, and the convergence of these red dots will be faster. Like for example, from my perspective here, we will just compare. I think the winning team about influence in this graph will be the orange team. Okay, because of this proximity. So it depends which model we use to learn about what. Is it just the impact of the ideas that we will want to propagate? And we can simulate the ideas and the propagation of ideas on the edges. Okay? Graphs is unstructured like this, but there is always a meaning from their structure, right? Sometimes we want to embed even the structure itself, like the distance between the nodes, etc. All this can be embedded. Images 2D is already a graph. Simply like this. 1D, 2D, 3D, 4D, they are all graphs represented by these connections, but they are stable connections. And because they are stable connection between pixels, we can delete this aspect. This feature will not help us a lot. The convolution already is doing a good job with the images because they are taking this mask, for example, for 3 by 3 pixels or 6 by 6, and they are convoluting over, and they are reducing the complexity of the big images to understand some aspect in it. So graphs is already representing the 2D images. 2D image is already a graph. Yes. Yes.
What are they thinking about it? Because what is triggered isomorphic when the data has stored different weights and
yeah. Isomorphic aspect, sometimes it's used because we have this aspect of labels of the data or the positions of the nodes. It's not important. And sometimes it's not useful because the positions are very important. The distance between the nodes are very important, and labels on these nodes are very important. So it depends even, again, on the context and how we do the representation of the graph. But the isomorphic aspect of the graph is already something very, very like important point to learn or to follow during the process. Thank you for your question. Thank you also. Yeah. Yep.
But how does the computer get satisfaction?
The satisfaction is to say to, I will simplify it to the most for sure, because you can create any rule you want. But if you say that the fitness or the function, to maximize the value of the rewards, like each time you win, you have +1. Each time you lose, you don't have anything, or you have -1, even you want to challenge them more. So by you make your rules and you say that you want to have the maximum points you need to achieve 10 points or 20 points or 100 points. And then you make the rule that if you step on the right, you lose -1. If you step and you if you step and you are able to move, you have +1. If you step and you face a wall like this, I don't want to break anything, you lose. You have 0 points or you lose, and he will learn based on these functions. And because his object is to win points, to do +1, +1, +1, +1 as fast as he can. So the iteration, first time he will say, okay, let's start like this. It will not work. and then you iterate, and it's very important, the process of reinforcing the iterations. And then he iterates. He said, okay, this time I did it like this, it doesn't work. He will check something else, and then something else. Everything is good, nice, let's continue. And then I will do like this. Okay, so I will iterate again. I know how to get +3, so let's do it. 1, 2, 3, and then what I will do, I will not repeat my mistake. Maybe he repeat also. There's a lot of examples that repetition of mistakes also sometimes is important. Sometimes he repeats some huge mistakes, and then he learns after. So this is the reinforcement aspect, and it's just about like gaming, like doing. It's very useful to build a maze game with your teachers to see this reinforcement learning aspect.
Yeah, I think of people that think of behavior reason, with the positive negative reinforcement.
Yeah. Values.
You need to have the highest score possible. So yeah.
Yeah, exactly. And you need always the plus, and when you repeat, try to seek these pluses. Yes. Sure. Yeah. There is a huge models of these just for chemical aspect. There is the chemical language models also. There is models today. As I said, there is genome language model. There is only genome sequences, CTA. I forget the fourth one. and it's for chemical aspect. There is a lot of tools that are behaving and they are managed to deal with. And sometimes we are inspired by this aspect because they already have this topological structure. They are concerned by this topological aspect of the graphs because the molecules and stuff like this. So they are doing such work, the chemical computer scientists, and they are doing a great work with this phenomenon. Yes.
AI research. What's your personal definition of artificial intelligence?
Sorry.
What's your personal definition of artificial intelligence?
I will give you my definition just when I will present my experiment, our experiment that we are doing. So for me, as again, we should always present things as a graph, because we should present its complexity, and because graphs is already image, it's already 2D data, and it's already 1D data. It can be represented as a graph. There is the order aspect. We talked about isomorphism, and not in the graphs. We can learn about this isomorphism. If it's important, we can embed it. If it's important, we can leave it if we don't need it in the context that we are working with. And the good point is that today we have this embedding of the graphs. This is the GNN process, how we embed the messages from the nodes to the neighbor nodes. Like, for example, A is related to B, and C is related to B. So A and C influence B to pass the message to B, that they are neighbors and they can be influenced. And then B can re-influence A, and we have to define how many levels we work in the graph at this aspect. But the main thing that I want to tell you about this is that transformers shift everything with the model of attention. And attention model is already thinking about the text, the 1D text, as a graphs. So let us see this example together.
As a transformer. Transformers don't read text from the start to the finish. They soak it all in at once, in parallel. The very first step inside a transformer, and most other language models for that matter, is to associate each word with a long list of numbers. The reason for this is that the training process only works with continuous values, so you have to somehow encode language using numbers. And each of these lists of numbers may somehow encode the meaning of the corresponding word. What makes transformers unique is their reliance on a special operation known as attention. This operation gives all of these lists of numbers a chance to talk to one another and refine the meanings that they encode based on the context around, all done in parallel. For example, the numbers encoding the word bank might be changed based on the context surrounding it to somehow encode the more specific notion of a river bank. Transformers typically also include a second type of operation known as a feed-forward neural network, and this gives the model extra capacity to store more patterns about language learned during training.
Okay, so transformers that make all this huge hype of AI with large language model is already, okay, the model of attention is already looking at the text as a graph. And I will add something to you to know it, and that not a lot of people out there know that this graph is a special type of the graphs that we just saw together. It's the fully connected graphs. Means we are obliged to say that each word, even if in the presentation or this video done by 3 Blue 1 Brown, it's a very amazing video that I really advise you to watch later on. Full course about the transformers, and they do a huge design to really present everything correctly. So GPT and BERT that use transformers is that they are using data, special type of data, which is fully connected word graphs. Fully connected word graphs. And if you want to make better models, like now when they want to reduce the complexity of the transformers, they are trying at least to say, okay, why we should have this 64 billion parameter or all these parameters, and the tokens and the relation between the tokens, they are trying to reduce it as much as they can. And this is what we do in the fine tuning. We reduce or we rechange the weights based on what really is our context, only on our data, on our sub-data with the fine-tuning. So if graph learning is dealing with complex graphs that are not fully connected graph, because fully connected graph is one type of graph, and we managed to do this huge impact with transformers, with a fully connected graph, which is one subcategory of the graphs, imagine what we can do with the graphs later on. And this is what I believe in with AI, that we should represent everything using the graphs. Graphs, I'm talking about graphs not fully connected, complicated, but not fully connected, because I don't want just a subcategory of the graphs. And then doing this graph learning efficiently with combining the graph learning with expert system, with combining them with rules, combining them with all the hybrid AI and symbolic AI that we can do, we are able to do something really more interesting. And what's appeared here for you? The word tokens. I'm not saying that. You can listen.
Computers speak numbers. Tokens are numbers. We tokenize almost everything. We tokenize images, words. Brett tokenizes motion, a sequence of plans that a robot performs. And so everything that we can tokenize, AI can understand. So we can tokenize proteins, and we can tokenize chemicals, we can tokenize motions, action, and behavior, all these things that Brent is trying to tokenize. We tokenize video, we tokenize 3D, fluid dynamics. Anything we can tokenize, AI can understand. And everything that AI can understand, it can translate, it can generate. And so that's the revolution that we're in. And that's why token is at the core of everything that we do. And ultimately, what we fundamentally do is to transform electricity into tokens. And that's what an AI factory does.
Okay? Transform electricity into tokens, transform text into tokens, transform images into tokens, transform chemistry into tokens. And what I don't agree with is one point is about when he say it's to understand and then to generate. Why we should generate? Stop with this, with the story of generate, because we need to understand first, and it's enough. Let's stop here. Why we should generate? For what? To make more noise in this world? So this part I don't agree with about generating, but understanding is mostly the most important part. Understanding the complex system, understanding the behaviors, understanding the context, the things, and not just like the flat data of text, audio, images, 3D, etc. And there is a lot of different models to do the graph learning and to embed data from, informations on the vectors and to be able to represent them efficiently. And it depends always on the context. Okay, so we can do a node embedding with deep work, with node to vector, from nodes to vectors, graph convolution network, graph sage, etc., etc. And graph neural networks appeared just in 2005, and it wasn't here before that. Graph convolution network came after, and then we have the graph attention network. The graph attention network is the attention model already, and there is a lot of tables like this that show you where we can use them and how these input this representation. And today, for sure, we are just talking agentic AI, beyond prediction, let's help with actions and so on. And it comes the story of our project that I would like to present to you, and I'm happy to present that in front of you and to get your insights about it. Our latest experiment is in this context. With the fast technology, here is what we see. Like, even if they are there, the 3% that you are looking at, they are still there, but it's a lot about the interaction between human and machines, and in particularly human and interfaces. Okay, you already are interacting with two objects, two, three, a lot of dashboards, a lot of tools, a lot of complexity. Notifications will come during my speech and during my talk. The same 1, 2, 3, 4, 5, if I would count it, 6, right? So in the operational context, whatever we are doing, even driving cars, industrial task, operation, it's all now look like, right? It was this like this with the airplanes since long time. But now everything looks like I'm in the cockpit of airplanes. This is too much. And this means that we will have to deal with that, all of us. Whatever is our task, we are students, researchers, engineers, etc., etc. Whatever it is. And this is what we are trying to do with the common project between neuroscience from a side and computer science or multimodal AI from the other sides and data analysis from the other side. Human artificial intelligence coupling in complex operation. High to co. Okay, high to cooperate. Human artificial intelligence coupling. Why? Because they are all afraid of this aspect. And they know what they are talking about. We are afraid of this, what's happening next. Aviation is talking about that. It's talking about that because the dashboard also for the aviation is changing. The interaction is changing. They are thinking about later on, do not have a pilots anymore. So what they will do, how they will do, can I drive 2, 3 planes at the same time, etc., etc. Automobile, we are in the autonomous cars already. Okay, and each time we have this automation, we need to build something to survey the human. Why? Because the car companies' veto was, yeah, we will do automated cars, but we are not responsible. So let's survey the human that is driving this car, even if it's automated car, he should be awake and he should be here and he should be fixing what's happening because he should correct anything that happened with the car. So this is on the operational aspect. The scientific subject is what? How really we operate and how really we interact with these complex systems. Okay, there is intelligence around us, but how we will interact with. Like the question that I can ask, and I didn't put it, but because I was planning that with my notes. In each day, you are using AI, right? Who don't use AI daily? Right? Okay. Who do not use 2 different AIs daily? Okay, only one. Okay. Who is not using 3 different AI daily? Okay, so we are all stuck with 2 different AIs. This is good, almost. And then you are making the decision, but you are interacting. Let's see on this platform. Let's see on ChatGPT what he will say. Let's see on DeepSeek what he will say. Let's see on Queen what will say. Sometimes I work with 5 different agents on my screen. Okay, this is without counting it, taking into account the GPS that we can now use 3, 4 GPS in the same time to check which one is really giving me the real update, live update. So the complex system is already here. It's already here. Between your own interaction with the machines and with all the agents that are today imposed in our life without deciding, but we are still efficient. We are still very efficient. And we will stay efficient. And we will model ourselves to see how we can profit from all that assistance correctly. So the idea is to bring cognitive science with multimodal AI in the context of operations. In the operational context. What is the operational context? I'm writing a report. I'm driving a car. I'm doing some industrial aspect. And to do that, as we said, it's complex systems. So a lot of micro modules, micro agents that interact. And now everyone is putting his force in this. We are not just really doing a simple project between scientists and doing the interdisciplinary project. They are all there here already. I don't know how to avoid them. Yeah, they are there. They are working also on some topics, in a different manner, not for the scientific aspect for sure. It's more about the takt time. We will replace later on even the drivers. Now we put outside 14,000 person in, and we said they are just doing secretariat. We don't want secretariat anymore in our workflow. And later on, we don't want even drivers. Yeah, they are jumping on this topic, all of them. And there is some papers, very, very recent papers like BADAS, context-aware collision prediction using real-world dashcam data. This real-world dashcam from cars. They are trying to understand this context to avoid the collisions. It's still a topic. Eye gaze tell you where you should compute. This is good, actually, almost. This is good. Why? Because they are saying, okay, so and all. Actually, the brain is doing like this, and we already discussed it. Our brain, like I'm not seeing anymore. There is a lot of chairs, even if I'm looking there. I'm not seeing a lot of chairs. That my brain is already focusing on your faces. So if you use this gaze data to make the vision models also always detect you instead of computing everything and computing even the brown aspect of the light here and stuff, this is more efficient for the computing. Vision language model, they are using eye gaze, and this is interesting. There is the, why it's not moving? Okay, sorry. There is the pan word model, but it's in the simulator. In the simulator, they are trying to understand everything, and they are saying that we can modelize. Now we are modelizing not objects, but the word. Modelize the word with word models, and this is just came out a couple of days ago, and we are for sure doing the show by saying our dear Jan Legun will leave Meta to make a startup and build this word model more precisely. This is what they are saying in the media, in journals. And we go to the context that we are doing our experiment with. I still have a couple of minutes. So in the industry, we at Icam, we have a production line, a real production line 5.0 with all the technology blended with this production line to build chariot car. Yes. And with different specification each time. And we have the physical flow, the operation aspect, and the numerical flow, the ERP, MES, the command system, and tick by light, RFID processing, and so on. All the industrial aspect that is already useful for this kind of technology, what we say Industry 5.0. But also we have a huge school of lean concepts. Lean concept is the theory developed by Toyota years ago. You know, Toyota, it was a textile fabrication. It was about carpet fabrication. And then they switch from carpets to cars. But before they switch, they had a real strict processing that imagine that you start a carpet, you know, carpet is a cumulative process. And you start the carpet and then you make the mistake at the end, before the ending the carpet at some point, you have to repeat everything and you have to throw it and repeat it and so on. So they did a very strict theory and processing, manufacturing processing, we call it lean aspect to sort, sustain, shine means cleaning the space, straighten means reinforce the place, and standardize. So the standardization. And we have this Kaizen concept, change for good, change good step by step, iterate over this change. We apply all this and we teach this aspect to the industrial in our school. And today we will profit from this teaching to look at the operator from a scientific perspective. And we will ask the question, again, the classical question, how we combine multimodal data source to represent the complexity of the task of assembling a chariot. And then mathematically, how to model this eye tracking, this task management system that we should do this, then that, then that, then that. And we want to see if we can aggregate these things together. So the first experiment we did is the cognitive load analysis with only the eye tracking. And then we registered data with Robert. Robert is our expert in lean teaching, lean mentor, and also he do lean audit and so on. So we did record data with Robert on organized workspace and unorganized workspace with Purple Lab that you have, I think, a lot here of them with your labs. So, and we study the data, what will happen to our brain by studying the eye tracking only. And we wanted to do that. Why? Because in the industrial context, it's very difficult to put EEG on the head, eye trackers, and being a cyborg, real cyborg in the industry, in addition to already what we are asking for. So, and in the literature, there is a lot of work about only eye tracking combined with EEG, EEG without eye tracking, or eye tracking plus EEG. But in the industrial context, for sure, we want the heaviest, we want the lightest process. So we study the eye tracking only with a pipeline. They take the audio, the object detection, the gaze and the fixation overlays, and so on. So we have now a platform. Yes, interesting to do it, and there is some work over this EEG, even telemetry. Means like I think about what I will say to you. You have the headset, and you have the same headset, and it transmits to you what I'm trying to say only mentally, without pronouncing or doing the motoral aspect. But no, in our exercise for now, we are not thinking about this aspect yet. Platform now that can combine the video analysis with the gaze and the fixation and the JSON file about the task, and we can select what we want to see on our output after. And we, during that, you know, there is this object detection in the video that is we face a problem with. We discovered that there is no images for the industrial objects. There is Coco ImageNet, sorry, as database, but there is no screw like the range to fix the screws and so on. So what we did, and this is what we will face most of the time, I suppose, we train a YOLO with a data set that we collect for object detection for the industrial aspect, and then we continue this task. So now we are able to, you can see it, right? We are able to see the hand tracking, the object detection, and the fixation of the eyes during the process. Between organized and unorganized workspace, we analyze these aggregation data. Is it I am looking to the same component, more time or less time? We can combine it also with other stuff that I will ask you to propose. And then we study this this aspect of correlation between object detection, fixation, the same object area. We see that he's not most of the time looking at this in the same area on the object side. It's looking just beside. And if we analyze the fixation matrix between organized and unorganized aspect, here you see the object detection, flange, nut, support, etc., and the null position. These are the time that our eyes were not looking to any object. There was no correlation between the fixation and the object. And we see that we are looking to null places more often when we are on unorganized workspace. And if we look just on the heat map of the gaze, we see that it's more sparse and small diameter with the object gaze heat map when we have unorganized field instead of less focus in the organized field. Some of you should jump and tell me, but usually when we are organized and unorganized, unorganized is more stress. More stress means more diameter with the bubble size. We are testing with an expert, so we didn't have this problem of the bubble size. He was even so zen, let's say, we can say zen, by doing the task, even if he was on an unorganized aspect. But what if we repeat this experiment with novice persons? In unorganized place, the values will jump to see a lot of difference between unorganized and organized. And this is, for the first time, we are saying to the operators, Kaizen, change for good or change good, step by step, iterate your change. It's not for the industrial aspect anymore, for production aspect anymore. It's for you. It's for your mental health, your less stress, your focus is simple. You can maintain your focus on what you want and how you want. And we aim to add more features to this experiment, and to also iterate it, etc. And with this experiment, with this discussions that we had, I would like to thank you and say that AI today that we are using are like philosophers with a lot of experience, not only 7 years old, but maybe more. But we are more in the specialized AI, agentic AI. But if you want really to switch, we need this mind 5.0, or the cyborg mind that can be augmented in this complex system operating between human brain and the operation context. Thank you so much. Thank you. Bye-bye.